In this video, we will be continuing our look at chirality, focusing on chiral molecules and how to name them. In particular, if we think about having a left-handed and a right-handed molecule, how do we specify whether we're talking about the left hand or the right hand? Let's look, for example, at 2-butanol. And so we have 1, 2, 3, 4 carbons, so that's why we have bute. There are all single bonds, that's why it is AN. We have an alcohol, which is why it has the OL ending, and that alcohol is connected to carbon 2, so this is 2-butanol. But you should recognize that this is a chirality center, which means 2-butanol can exist in this configuration where the OH is coming forward, H is back, or in this configuration where the OH is back and H is forward. So 2-butanol isn't specific enough. We need a way to be able to distinguish these two compounds. So what we use is called the Cahn-Ingold-Prelog system, named after 3 chemists who developed this, the Cahn-Ingold-Prelog rules. And so we have to assign priority to the different groups. So in general, the higher atomic number is higher priority. Higher atomic number is the higher priority. And then ironically, the higher priority gets the lowest number. If you have 2 points where you have the same atoms, move out 1 atom at a time. And if you have double bonds, they count twice. So let's assign priority to the groups connected here. So we're focusing on this carbon, and what we have connected to it is an oxygen, a hydrogen, a carbon, and a carbon. Oxygen has the highest atomic number, so this is priority 1, highest priority. Hydrogen has the lowest atomic number, and so this has the lowest priority, priority 4. Now we have a carbon compared to a carbon. These are equal to each other. So now we move out 1 atom at a time. So this carbon is connected to HHH, whereas this carbon is connected to HHC. So this carbon and this carbon are the same. So then we focus on the fact that this is connected to HHH, whereas this one is connected to HHC. C has higher priority than H, so this group has higher priority than this group. So that means our ethyl group is priority 2 and our methyl group is priority 3. Now, once we have assigned priority, then we need to trace the priorities 1 to 2 to 3 with the lowest priority in the back. So the lowest priority in the back, and then we trace 1 to 2 to 3. If we trace clockwise, that goes with the Latin rectus, R, and if we trace 1 to 2 to 3 counterclockwise, that is sinister, which is S. Okay, what the heck does this mean? So we have assigned priorities, and we have 1, 2, 3, and our lowest priority 4 is going back. Once we've confirmed that our lowest priority is going back, now we can ignore priority 4. So we're going from 1 to 2 to 3. We trace that we're going clockwise. So this is going clockwise, so this has the R configuration. So the compound on the left would be R-2-butanol. 2-butanol, because we have 4 carbons, it's an alcohol at position 2, and carbon 2 has the R configuration. We are going to use the Cahn-Ingold-Prelog priority rules a few different times this year, naming different types of compounds. So we're always focusing on the higher atomic number. Now, if we look at this compound, we can again assign priorities, and the priorities are the same because oxygen has the highest priority, ethyl will have a higher priority than methyl, and then hydrogen has the lowest priority. So now that we have our priorities, we need to trace 1, 2, 3 if 4 is in the back. But in this case, priority 4 is in the front. So if our lowest priority is not in the back, we have a couple of options. One is that we can manipulate the molecule to put the lowest priority back. So this is why I have you practicing how to manipulate molecules. So right now our hydrogen is in front. If we pick up this entire molecule and rotate it around this way, so we're just rotating it front to back, like we're turning the page. So if we do that, that puts the hydrogen back and the OH in front. That puts the methyl group on the right side, so I'm just using Me for methyl, and the ethyl group on the left side. So hopefully this is just a different representation of the same compound if I did this correctly. Now, if I did this correctly, this should still be the same compound, just in a different orientation, where now our lowest priority is back. So once again, 1, 2, 3, and 4. And our lowest priority is back. So now if we trace 1 to 2 to 3, now we are moving counterclockwise. So that means that this carbon has the S configuration. So this compound then is S2-butanol. So by assigning R or S configuration, which really means we are interpreting what is the orientation of the groups. By assigning R and S configuration, we can be more specific about which compound we are talking about. Now, let's come back to this again, because if our lowest priority is not back, either we can flip it over, put the lowest priority back, and then assign configuration, or we can break the rules a little bit, where looking at 1 to 2 to 3, this is clockwise, which would lead to R, but because our lowest priority is in front instead of in back, then we change the assignment to S. In other words, your options are flip the molecule and then assign, or assign and then flip the assignment. What we see is that a chiral molecule and its enantiomer have opposite configuration. One is R and its mirror image is S. Let's keep looking at a few more examples and try to determine the configuration so that we can use that as part of the name. So here is our chirality center, here is our chirality center, here, here, and here. Looking at the first compound, focusing on the different groups, we know that hydrogen is the lowest, that's going to be priority 4. Bromine has the highest atomic number, that's going to be priority 1, followed by chlorine, followed by carbon. So we have priorities 1 bromine, 2 chlorine, 3 carbon, 4 hydrogen. Notice our lowest priority is back, so all we have to do is trace 1 to 2 to 3, and we are going clockwise. So the configuration of this carbon is R. So the full name of this compound would be R-1-bromo-1-chloroethane, right? Because we're actually naming it as ethane with a bromine substituent on C1 and a chlorine substituent on C1. and then we have to specify the configuration, R. For the next one, we have the same groups, so bromine, chlorine, methyl, and hydrogen. But our hydrogen is neither in front or behind, it is in the plane. So we have a couple of options once again, and some of this depends on how you can visualize this. Imagine holding this carbon and this carbon in the plane, but rotate around this bond. So if we rotate around here, then we're keeping our CH3, here's our C. Actually, let's think about it as this is a steering wheel, and we're going to turn the steering wheel. Let's go counterclockwise if we're looking at it from this side. If we turn counterclockwise, then that is going to move the hydrogen toward the back. That moves the bromine this way, and the chlorine moves from the back to the front. So our bromine is going to come down here, our chlorine is up here, and our hydrogen is here. Now we can look at 1 to 2 to 3. We are going counterclockwise, so this one is S. Alternatively, what you can try to do, instead of having to rewrite the molecule, you can just move your perspective. So imagine that you are looking here, looking down this bond. Remember what this means. The bromine is in front of the screen, the chlorine is behind the screen. If we are looking from here, that puts the hydrogen back behind, and the bromine is going to be to our right, the chlorine is going to be to our left. So going from bromine on the right to chlorine on the left to the methyl, right to left to down, is counterclockwise, which is S. Now, when I look at these, when I think that I am looking down here, I usually will turn, like I'll put myself to the side of the board so that I'm looking at it that way. And even as I was recording this, I was turning my tablet and looking at it down that way, right? Because now this is in front, this is behind, and this is to the right. But if I'm looking from here, then this is behind, this is to my right, and this is to my left. And again, I keep turning the tablet to be able to see it in that way. So you need to find what is going to work for you, whether it is more helpful to move a molecule or to move your line of sight to be able to figure out whether a certain chirality center has the R or S configuration. In our next example, we are looking at a hydrogen compared to carbon, carbon, carbon. This carbon is connected to 3 H's, this carbon is connected to 2 H's and a C, this carbon is connected to 2 H's and a C. So these two have higher priority than this one, but now these are the same, so we go out one more atom. This carbon is connected to 3 H's, this carbon is connected to 2 H's and another carbon. So this has priority 1, 2, and 3, and then hydrogen is priority 4. So with our priority 4 coming forward, if we go 1 to 2 to 3, we are going counterclockwise, which would be S, but because we have to change the configuration, that makes this R. So this compound has the R configuration. Looking at the next compound over here, I'm going to fill in the hydrogen that is going back behind. And now let's think about priorities. So hydrogen has priority 4, and then we're comparing carbon, carbon, and carbon. So let's look at the next set of atoms. So this is connected to hydrogen, hydrogen, hydrogen. This carbon is connected to hydrogen, hydrogen, and then this carbon. This carbon because it's double bonded to a carbon, it's as if it's connected to a carbon and another carbon and a hydrogen. So carbon, 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 but this carbon is connected to two carbons, which gives it higher priority than this carbon connected to one carbon, which has higher priority than this carbon connected to three hydrogens. So this is priority 1, 2, and 3. If we're going 1 to 2 to 3, we are going clockwise, and our lowest priority is back, so clockwise R configuration. And in our last example, here we are looking at carbon, carbon, carbon. The top carbon is connected to three hydrogens, so we know that's going to have a priority that's lower than the other two sides. So this is priority 4, this is priority 3. But what about this carbon compared to this carbon? Now, it might be tempting to look at, okay, here we have an OH, here we have a carbon that's connected to two oxygens. So with the two oxygens, that has higher atomic number, so that's got to be a higher priority, right? But keep in mind, the rule says that if you are looking at the same atom, then you move out one atom at a time. So we compared this connected to three H's, this connected to two H's and a C, this connected to two H's and a C. So now we will move out one atom, and now we're comparing this carbon with this carbon. So the green carbon on the left is connected to H, H, O. The green carbon on the right is connected to H, H, C. So it doesn't matter that we have a couple of oxygens down here. We don't get that far in terms of determining the priorities. We go out one atom at a time until our first point of difference, because this green carbon is connected to things that are different from what this green carbon is connected to. We can already assign priority. So this carbon has higher priority than this carbon, which means the group on the left has higher priority than the group on the right. So now we have our priorities 1 to 2 to 3. We are going counterclockwise, which would give us S configuration. And since our lowest priority is in the back, we stop there. So with these examples, we have applied probably all of the rules that we're going to need to apply. To assign priority, we are looking at highest atomic number. We move out one atom at a time, and we have to remember that multiple bonds count as being connected to that atom multiple times. Once we have assigned priority, when we want to then assign R or S configuration, if the lowest priority is back, then moving 1, 2, 3 clockwise gives us R. Moving 1, 2, 3 counterclockwise gives us S. In an earlier video, we looked at the compounds menthol and cholesterol, and we identified chirality centers. So in menthol, keep in mind we have a chirality center here, here, and here. In cholesterol, we have here 4, 5, 6, 7, and 8 chirality centers. So I want you to practice and assign RS configuration to just a few of these chirality centers. So on menthol, try this one and this one. And for cholesterol, try this one, and this one. These offer a good challenge without being a really demanding challenge. By the time you get to some of these, we are moving so far out that it really gets hard to follow. So just try a couple more and we will talk about those in class. Now, before we move on, I want to make sure that you all are clear on configuration versus conformation. So configuration, we are talking about the relative arrangement in space that are defined by the Cahn-Ingold-Prelog priority rules. And we cannot interconvert one configuration to another. If something is R, we cannot change it to S unless we're doing a reaction or we're breaking a bond. With conformation, we are talking about the relative orientation in space, so that sounds very similar to configuration, but we can convert one conformation to another by rotation around a single bond. So with conformations, this is where we're talking about eclipsed and staggered, we're talking about cyclohexane chairs, and we think about rotation to interconvert between different conformations. Configuration, this is where we are talking about the specific orientation of a particular set of atoms around a chirality center. Now, a few slides ago, we were looking at focusing on a pair of molecules, determining the relationship. Here we have a chirality center. This is connected to H-methyl-ethyl-OH. Here's our chirality center, H-methyl-ethyl-OH. So this chirality center is connected to the same four groups. So either we have different representations of the same compound, or we could have a pair of enantiomers. What we did on the other slide was look at how can we manipulate this molecule to put it in the same orientation as this one so that we could compare and figure out whether they're the same thing or mirror images. But now we can do it a little bit more quickly. Again, this only works if we are comparing the same groups, right? In OH, OH, ethyl, ethyl, methyl, methyl, H, H. Let's assign configuration. So first with priority, we have the OH, followed by the ethyl, followed by the methyl, followed by the hydrogen. Our lowest priority is in back. So if we go 1 to 2 to 3, this is clockwise. So this is R. Over here, we have priority 1, 2, 3, and 4. Our lowest priority is forward. So if we go 1 to 2 to 3, this is again clockwise, which would be R, but because our lowest priority is forward, we switch assignment, so this is S. So rather than having to manipulate this molecule a bunch, we could just assign RS configuration and we can more quickly see that these are enantiomers. Now with this pair of compounds, we have priority 1, 2, 3, and 4, 1, 2, 3, and 4. We want to try to look at it from down here so that the hydrogen is back behind. And remember, this bromine is in front of the plane. So if we're looking at it from this way, that's going to be on the left. And then the chlorine is on top. And then the methyl is on the right. So we are moving clockwise, which means this is the R configuration. Now, even though this one is written in a different way than these others, we have our lowest priority back. So that's what matters. Now, if we go 1 to 2 to 3, this is clockwise, which is R. So these two have the same groups attached. They have the same configuration. Therefore, they are just different representations of the same molecule. So assigning R or S configuration is necessary to be able to name a compound, but here we can see that it can also be useful to be able to compare two representations.